All right, guys. Sorry I'm a little late. So today we're going to start where we left off yesterday. Remember, at the end of yesterday, in the middle of yesterday, we saw there were two interesting facts that were exposed by thinking about the fan of the normal fan of the associahedron. One of them was that, of course, the normal fan of any polytope gives you a bunch of cones that tile all of space, and the cones. Oh, sorry. Mike's not on. Is that okay? All right. Of course, the normal fan of any polytope gives you a bunch of cones that tile all of space, and that you can think of each cone as associated with the vertices of the polytope. But that sort of preassumes that the associahedron was handed to you via the construction in Carolina's lectures, for example. So the first comment that we got through yesterday is how to get at least the rays of that cone from nowhere, right? Starting from a picture of the surface, just recording the data of every curve on the surface by these words with left and right turns, and extracting the g-vectors for the curves from those words. And that just plonks down a bunch of cones, plonks down a bunch of rays, which turn out to bound cones that can be interpreted in terms of triangulations, and which collectively cover all of space. The second, maybe even much more striking observation, was that you could generate all of these cones, the rays and the cones, and they're associated with these polynomials that we talked about. And their tropicalizations gave you a bunch of piecewise linear functions that a few of them, that when you put them all on top of each other, the domains of linearity of these piecewise linear functions broke the space up into all these cones, each one of which corresponds to a diagram. And which we could think of as being put together into the integrals that we wrote down as giving a sort of global version of Schwinger parameterization, some kind of one single integral that, as you moved around in the whole space, morphed in piecewise linear region by region, cone by cone, morphed into the Schwinger parameterization for the corresponding diagrams. And the pre-tropicalized version, with just the polynomials that we talked about sitting there, were instead string amplitudes. So this is the sort of connection. What I'd like, by the end of yesterday, we talked about where the g-vectors come from. And what I want to start with today is telling you where those u variables come from. And because of the time, I'm not going to be able to prove to you that these variables do what they're supposed to do. But I'm going to describe what at least one motivation for where they come from. This motivation will still maybe seem slightly alien if you haven't seen anything like this before. But at least you'll see a very simple sort of combinatorial problem associated with these words naturally leads you to think about these u variables. I could just give you a formula, as you'll see in 15 minutes. It'll be a formula taking a product of a bunch of 2x2 matrices that's going to produce these u variables. But I want to at least give the counting problem motivation for this, not just because it's cool, but because if you go away and think more about the counting problem, it'll make it clearer why these objects do what they're supposed to do. Okay, so you can really just think of this as a recipe for producing these u variables. Okay, so we're going to start with getting the u variables. And again, remember, all of our life, our universe, is specified by this fact graph. Okay. So for the process, you draw one representative diagram that represents the sort of flow of color, and then everything else lives in this world. And if we talk about a curve, we decided that a curve was one of these trips through the fact graph. And so this curve 2, 4 would have the word that we described as 2, 3 makes a left turn onto 1, 3, makes a right turn onto 1, 4, makes a left turn onto 4, 5. And we also discussed how we could draw it as a mountainscape. 2, 3 goes up to 1, 3, goes down to 1, 4, goes up to 4, 5. Okay, so these are two different ways of representing exactly the same word. Okay, so now I'm going to define a counting problem associated with any word. Forget about all this. We're going to say a counting problem that are associated with words. And this is what we're going to do. Let's say you have a word that looks like A, B, C. I'm going to tell you what the counting problem is. You just want to choose sort of every object that you see in this word. So, for example, I could choose to I want to pick every letter that I see in this word in every combination. So, for example, I could choose to pick nothing, and I would write down 1. So I could make a generating function that goes with that. Okay, so I could choose to do nothing. I write down 1. I could choose to choose A by itself. I can choose to choose C by itself. I can choose to take A and C. But if I choose B, I have to choose everyone who's downhill from B, right? So I used to call this the relationships with baggage generating function because it's like, it's like dating. When you date someone, you kind of like dated everyone that they've dated before. Okay? So if you choose B, you have to choose everyone in the sort of past light cone of B. So you have to do plus B, A, C. All right, is that clear? So if we do another example, let's say it's A down B up C. What is this? This would be, again, I could choose nothing. I could choose B. I could choose A, but if I choose A, I have to choose B as well. If I choose C, I have to choose B as well. I can choose A and C together, of course. Then I still have to choose B. Right? Is that clear? All right, now it's sort of obvious from high school how you can compute. I mean, you don't have to do it this way. It's possible to compute this function, this generating function, in an obvious way recursively. Okay? So, in other words, let's say you give me a word. I can kind of start from the end and get the generating function related to the one shorter word, where I peel off an end. Now, how does that work? Well, let's say that, so I'm going to call these objects F associated with the word. They're not quite going to be these F polynomials that we'll talk about later, but anyway, let me just call them F. So let's say I have A, and it goes up, to some B, and it's going to do something else. There's sort of rest of the word there. Okay. What we're going to do is divide this generating function into two pieces that I'm going to call F yes and F no. Okay, so F yes is does it choose A, and F no is does it not choose A. All right, so there's F yes and no, according whether it does or doesn't choose A. So what is F yes? Okay, well F yes is it chooses A. Okay. So F yes is because it chooses A, it's going to have a factor of A there, right? But if I choose A, then here the question is, do I have to choose B or not? Right? And well, I can choose B or not choose B. It doesn't matter, right? So I'm going to call the rest of the word here is going to have its own little f. So it has its own little f, yes and no, where this yes or no refers to B, right? Call this B, right? So this is A times little f yes plus little f no. It doesn't care either way. Okay? Is that clear? On the other hand, if I don't choose A, well, I'm not going to have anything here, right? I'm not going to have A. But I definitely could not have chosen B, because if I choose B, I have to have A. Right? So this is just equal to F no. Right? And so we immediately learn something that F yes and F no is this little 2 by 2 matrix, AA01 times little f yes and little f no. So when I turn up, I get that little 2 by 2 matrix. Okay? So I'm going to call this m left of A. Right? Well, similarly, if I go down, let's just do it quickly here. If I go down, A down to B and the rest, then f yes of A is equal to A, but since B is downhill of A, I must have B here, so this is f yes. And meanwhile, f no is the thing which, again, I could take either one. It could be little f yes plus little f no. So this is turning left from A. And so we also similarly have a matrix for turning right from A, right? So we have f yes and f no for turning right from A. Is this other matrix, A011 times little f yes and little f no. So we'll call this matrix M right of A. Okay? And so this tells us how to build this F. I just take the product of these matrices, right? I take the product of these matrices as I go down the word. And then at the very end, I have f yes and f no. I can add them if I want to get the full f. Okay. Now, if you remember, our words, coming back to our context, they're open curves, and so they're kind of special in that they start and stop somewhere. Have some boundaries. And then I leave it as a very small exercise. It's very, very obvious. But I'm going to leave it as a very small exercise to show that if I have a word that's like alpha as a boundary, and it goes turn, I'm going to move turn is left or right, okay? Alpha turn and some road A1 turn and A2 turn, okay? And it's going to go finally some turn beta, so alpha and beta are the ends, okay? Okay, then there is I can look at the sort of f that I would get from this big word. But in this big word, it's also natural to look at which part of f includes both alpha and beta, which part includes only alpha, which part includes only beta, and which part includes none of them. All right? So I'm going to group those things. Let me call them to f has yes on alpha, yes on beta. F no on alpha, yes on beta. F no yes on alpha, no on beta, and F no on both. Okay, so this is a 2 by 2 matrix, and it's a trivial consequence of what I just told you, that this matrix is in fact the product of all of these matrices. Okay, so this is the product of the matrix for turn at 1, turn at 2, okay, up to turn of whatever it was that we had. Okay. Let me be a little more precise. So if I take this matrix and for this first matrix, if I turn left or right, I'd have to put the M for alpha, right? But here you have to put alpha equals 1. And you imagine that this is sort of beta equals 1 as well. Of course, beta doesn't show up. There's no term that depends on beta. Beta is the last thing. Okay? So if you look at this matrix and set alpha to 1, of course, beta is tacitly to 1. Then you get an entry here where this would be, to get the real word for this that would have an alpha and beta, just multiply this by alpha beta. Okay? So this is, so these are the sort of coefficients of the alpha beta term, the coefficients of the beta term, the coefficient of the alpha term, the coefficient of none of them comes simply from taking the product of these matrices. Okay? So this is a matrix that's attached to any word. Now, Now, if we stare at these matrices, sorry, I partially erased it. Notice that each one of these matrices has as a determinant that's just given by A, right? So the determinant of this matrix is A, the determinant of that matrix is A. And so one thing which is obvious is that the determinant of this matrix associated with any word, if we imagine that those variables, the ABCs, are just positive, the determinant is positive. Okay, so the determinant of this matrix associated with the word W is just the product over all these, all what I call there, the little a's, all the sort of AK. And this is positive if the AKs are positive. So which we'll be assuming. So if I look at this matrix, so this is a matrix that has a 1, 1, 1, 2, 2, 1, and 2, 2 entries, then I know that M1, 1, M2, 2 minus M1, 2, M2, 1, the determinant is the product of all these A's is positive. And therefore, the ratio U associated with this word, which is M12, M21, divided by M11, M22, is less than 1. And of course, if all of these variables are positive, clearly as I multiply these matrices, they're all plus signs here everywhere, these simple matrices. Okay? This U is also going to be bigger than 0. Greater than or equal to 0, less than or equal to 1. That's the U variable attached to a curve. Okay. So if you give me any word for any curve on any surface, all you do, you just build the word, you multiply the 2 by 2 matrices associated with the entries in the word, and you take this ratio, 1, 2, 2, 1, off diagonal over diagonal, and that gives you the U variables associated with the curve. So I'll leave it as an exercise for you to do this for the little 5-point problem. You'll have to multiply at most 2 by 2 matrices and take the ratios and discover those U variables that we wrote down yesterday. All right? Okay. Now, and that's all I'm going to say about it. Maybe one point to make is that this is sort of presented as sort of manifestly a ratio of polynomials, right? All of these things are sort of ratios.
Could you say one more time what the variables are?
Oh, the variables will be associated with what we call the y. So let's just write down again this example. Okay. So back to this example. You would now go and label the internal rows not just with a name but also the variable y. So there'll be a y13 that goes with this row, and a variable y14. Okay, and then you again take your favorite curve like 2, 4, which is now the word would be y12 up 13 down 14 up 4, 5. Okay. And now the matrix associated with this word, the matrix associated with the word M24 is, this is up at 1, 2. But remember, this I'm supposed to set to 1. So the up matrix was AA01, but A is 1 here for this one. Okay, so I'm starting at the boundary. So this is 1, 1, 0, 1. Then at 1, 3, I turn right. So here I put the matrix Y13, 0, 1, 1. At 1, 4, I turn left, so I put the matrix Y14, Y14, 0, 1. Okay? So this gives me a 2 by 2 matrix. And the U for 2, 4 is going to be YZ over XW. Which if you did it in this case, you would discover is 1 plus Y14 plus Y14, Y13 over 1 plus Y14, 1 plus Y13. Okay, you can see how these things are built up from products of these 2 by 2 matrices. See, these things look like relationships with baggage generating functions. Okay?
Very quick question.
Okay.
Is this
yes.
2, 5 or 2, 4?
Sorry?
Is this path 2, 5 or 2,
this path is to 4, because it's 1, 3, to 2, 3, left on 1, 3, right? Then I turn,
We started at 1, 2.
oh, I'm sorry. I just wrote this wrong entirely. I'm sorry. So I'm starting at 2, 3. Sorry about that. At 2, 3, left on 1, 3, right on 1, 4, and then left on 4, 5. Sorry about that. Is that okay?
No. But I have a question.
Yes, yes.
2 questions, in fact.
Sorry?
2 questions.
Yes.
Can I ask them?
Yes, you can ask them. But you can't ask 3 questions. There's a sharp upper back.
Okay, so the first question is, what kind of geometrical resolution or precision we obtain on the 2-dimensional trajectories within the formalism used?
Oh, there's no geometry here at all. This is pure. There's nothing about what this curve looks like at all. This is just a labeling for what the curve looks like. So it has nothing to do with that.
Yeah, thank you for your answer. And question number 2 is directly related to the observation you just made publicly. Where does this formalism first arise from? I mean, physics or maths?
Both. I mean, although I should say that these variables are closely related to many other variables that have been discussed. They're very closely related to X cluster variables for surfaces, a la Goncharov. They're related to cluster variables, X cluster variables, but there are very special sets of them, and this particular way of thinking about them and focusing on them is new and was very much motivated by physics. Okay. The thing is that you can talk about cluster anything you like. It's these variables that turn into the Schwinger parameterization of all diagrams and string amplitudes and so on. So these things that go from 0 to 1, they satisfy these remarkable u plus u equals 1 formulae. That's the they realize in this binary way the combinatorics of compatibility, whether curves cross or not. Okay, so that's that was very much motivated by physics.
Professor
Actually, I'll just make since the question was partially historical. These variables, literally these variables, for the context of studying string amplitudes at tree level, were discovered in string theory before the standard formalism for doing string calculations. Okay, there's a famous formula called the Koba-Nielsen formula, and these U variables were described by Koba and Nielsen in 1968. Okay, and they were very excited about them exactly because they made factorization manifest. Okay, that's only later that Koba and Nielsen themselves realized that you could formulate the problem instead in terms of sort of cross ratios of points on a disk, and the picture of a string worldsheet began to emerge. And then the string worldsheet picture kind of took over because you could make it systematic, you could do it for any surfaces, think about loop corrections, so lots of things came from that picture. And this more algebraic and the way that sort of centered on curves on surfaces was entirely forgotten. And what's happened now is 2 things. First of all, we understand that they also make sense for all surfaces. Okay? So there is no loss in going back and forth. So all those physical things that Koba and Nielsen were excited about are actually there and present and useful, not just at tree level, but for all surfaces. But maybe more importantly, Koba and Nielsen found the U equations, and they even found how to solve them. But they only found how to solve them in this way that I mentioned yesterday, this most direct way, solving for the u's in terms of the u's, which you can only do in some cases, and it's very artisanal, and definitely you couldn't imagine doing it for more complicated surfaces. Okay? So the second novelty here is the solution of the U equations. Like we're telling you how to solve them by associating these counting problems with the curves on the surface and the product of these matrices and so on. Okay? So it's both the fact that they exist and that they're concretely available. Okay? And what they do, what the U variables do, is they give a sort of completely algebraic way of thinking about what not just the moduli space, really the tabular space of these two-dimensional surfaces, but also what the compactification of these spaces, how you add back in all the boundaries. And what's novel about it is it's done in an entirely algebraic way. You just write down all these equations and you just declare the u's are positive and you're done. The usual way of thinking about the compactification of these spaces, even in sort of a clustery way of thinking about things, or the Faku-Goncharov way of thinking about things, is more local. It's synthetic. You go to the neighborhood of a boundary and you figure out how to sort of complete things in the neighborhood of that boundary, so patch by patch. This is not patch by patch, and it's a very practical advantage. It's conceptually interesting, but it's also practically important. That's what allows us to write down one integral. Done, right? And that one integral blows up all the singularities and tells us how to just go ahead.
Could you say a word about finite?
Yeah.
When you in the example are always at this 5-point example.
Yes, yes.
But as soon as we do something more interesting, everything will be infinite.
Yes,
Can
yes,
you
yes.
comment on finite? That bothers me.
Yes, yes,
Can
yes.
you comment
Absolutely.
on finite versus infinite?
Absolutely, absolutely, yes. So what Bernd is referring to is that the moment we get to more interesting surfaces, and actually, you have to get, it really starts with the annulus. Okay? So the problem has nothing to do with these variables per se. The problem has to do something about curves on surfaces. So if I think about this picture of an annulus, I could draw a triangulation of the annulus. This is a slightly degenerate triangulation, but I hope you can see this is a triangle, right? This is a triangle, and this is a little triangle here, right? They all have 3 sides. That's the important thing. The triangles have to have 3 sides. They don't have to have 3 vertices. They have to have three sides. And that's what lets them go along with cubic graphs. Okay? So, well, what cubic graph would go along with this picture? If this is 1 and 2, the cubic graph that goes along with it would be this little picture of an annulus. Okay? So this line 1 is what's going around here. Okay, so that would be sort of region 1 or line 1. This is region 2 or line 2. Okay? Okay? And now what Bernd is talking about is the following. You see, at this level, this triangulation is this diagram, but there's one diagram here. Okay? There's a single diagram. But here, I could take this picture and I could just twist everything. Okay, I could just twist everything once, and clearly it's going to look a little more wound around. I'm not going to try drawing it. I could twist it any number of times, okay, this way, that way. So on this side, there's an infinity. There's infinitely many triangulations that just differ by winding or Dane twist. Or this is the action of the mapping class group on the surface. But if you haven't heard these words, it's just the obvious picture of winding here. Okay? And that's completely absent on this side, apparently. Okay? So it looks like, and the point is, of course, that precisely because all of these things are related to each other by winding, they're combinatorially exactly the same. They're all this triangulation. But thought of as in terms of curves on surfaces, there's infinitely many of them. Okay? So this seems problematic at first. It's actually a blessing in disguise. One of the reasons that it's a blessing in disguise is that, remember, I mentioned early on that as physicists, we would like to imagine putting all the diagrams together, even at loop level, and putting them under a common loop integration sign to sort of identify what we mean by loop momenta from diagram to diagram to a diagram. And I said that when it's planar, there's a sort of way of doing it. But when it's not planar, there isn't. There isn't naively a consistent way of labeling loop momenta that allows you to combine all diagrams together. But in fact, there is. And the curves on surfaces exactly tells you how to do it. You draw for any diagram is some triangulation, right? So you draw the curves on the surface, and then for any curve, you read off the momentum associated with that curve by homology. Okay, so we saw it already, we didn't say it in this slightly fancy language, but already here, when I draw, even in the disk, when I draw something like that, I draw this curve. And I say the momentum associated with that curve that I squared to get the x associated with it is P1 plus P2 plus P3. But you can sort of think that I assign momenta to these boundary components, and the momentum of this guy is the same as the sum of those guys because this curve is homologous to these. I can continuously deform it to the boundary. Okay? So in that way, you can take any surface. Now, in a case like this, you see, this curve, for example, this curve can't be continuously deformed to the boundary. So you have to give that one a name. So we have to come up with an element of the homology. So this curve, I'll give its momentum a name. I'll call it L. But then this curve is going to be L plus the momentum associated with particle 2. Okay, so this curve would have momentum L plus the momentum particle 2 is Q. If it wound around twice, it would be L plus 2Q, and so on. Okay. And so that actually gives you a completely consistent way of labeling what you mean by momenta, including loop momenta, for any diagram, right? What's the catch? The catch is that there's now infinitely many diagrams. Okay? There's now infinitely many diagrams, so that when you do the action of the mapping class group, what it does is it doesn't leave the loop momentum invariant, right? It'll shift the loop momentum. For example, if I wind here once, the loop momentum will shift by L goes to L plus Q. Now, of course, since I'm integrating over the loop momentum, the amplitude doesn't change. That's the point. But we've sort of found a way to solve this essential, kinematic problem, how you label momenta, directly from homology of curves on surfaces, at the expense of having infinitely many diagrams. Okay, so but that's a sense in which it's a good thing, right? That at least it's a first step to letting us put everything under the same sign. So now all we have to do, quotes, all we have to do, is mod out by the mapping class group when we're done. Okay? And that's what we actually do. We take this whole formalism. For any surface, we have the product of u to the x. Including when there's loops, it's the product of u to the x. When there's loop, the x's will contain loop momentum in them, and this u to the x will have things that are quadratic and loop momenta upstairs. Again, this looks exactly like Schwinger parameterization, if you're familiar with it, either in physics or math. So we can do the loop momenta, they're Gaussian integrals, that's exactly the Schwinger parameterization point. So you're still left with an integral over the y's, now you're done integrating the loop momentum. So whatever you're left with and you're integrating over all these y's is mapping class group invariant because you've integrated over the loop momentum. Now it's totally mapping class group invariant. So all you have to do is now mod out by the mapping class group. Okay. And you might think that modding out by the mapping class group would involve, maybe identifying some fundamental domain that then sort of covers the entire space after you do the action mapping class group. If you wanted to do that, it would not be such a fun thing to do. But there's much simpler ways of modding out by the mapping class group. So what a physicist would call the Faddeev-Popov trick, what mathematicians would call the Mirzakhani kernel, okay, are very straightforward ways of just modding out by the mapping class group to get the answer. Okay, so beyond at tree level, we don't run into this phenomenon. Even at one loop, we don't run into this phenomenon. But starting for the annulus and beyond, this thing that Bernd mentioned about the infinity is ubiquitous. But the infinity is a good thing somehow across the board. If we didn't have infinitely many curves, these U equations would not make sense. We really need every curve on the surface for these equations to make sense. Not only the ones that wind infinitely much, even the ones that intersect themselves. I mean, every conceivable curve on the surface shows up when you write down these.
So no way for me to look at the first 25 in a meaningful way.
Let's
say I want to look at the first 25 variables and 25 equations. How should I list them?
Yeah, that's right. Yeah. So one of the this is one of the things that makes us very, very practical. There is infinitely many curves and so on. It's true, but the way it's presented makes it clear you have these ratios of polynomials, and there is a sort of concrete sense in which you start with your parent graph, right? You draw the simple curves. Well, the simplest curves are the ones that occur in the triangulation. And then the ones that, by simple I mean literally the length of the word. How long does the word get, okay? Then as the words get longer and longer, the U variables associated with them get closer and closer to 1. Okay? Remember, they're stuck between 0 and 1. Okay? And so if the y's are, for example, if the y's, just to say a super concrete statement, if you think about the U variables as a Taylor expansion in the y's, okay, the ratios of polynomials, you can certainly Taylor expand them in y's. Of course, the y's go from 0 to infinity, but somehow the y's close to 0 means that your in the neighborhood of the surface degenerating to the triangulation that you started with. Okay? So if you just look as a Taylor expansion in Y, at any fixed order, the Taylor expansion, a finite number of curves have U not equal to 1. Okay, so first of all, in a sort of super precise sense, you need a finite number of curves at any order in the Taylor expansion. Secondly, even if you let Y's be anything, but some fixed number, you know, I have 10 Y's and the Y's are 17, 23, I just fix some fixed numbers for them. As the words get longer and longer for those fixed Y's, the U's for longer and longer words approach 1 exponentially quickly. Okay? So these U's are sort of they're very practical. If you want to sort of numerically evaluate these integrals, you don't need infinitely many of them remotely. You really need a small handful of them because of how exponentially quickly they go to 1. Okay? Yes?
So these are like some Teichmuller spaces. These spaces have some dimension. Do I know how many views I need?
There's infinitely many U's. In principle, there's infinitely many U's. Okay. In principle, there's infinitely many U's. If you want to write down a string amplitude, okay, it's your choice what U's to put into these formulas. Okay, because first of all, there's infinitely many curves, partially because even given any one curve, when the surface is interesting enough, it can go around and self-intersect itself lots and lots of times. So there's all the sort of self-intersecting friends of a given curve, right? They're there, they have U variables associated with them, but notice if a curve intersects itself, its U can never go to 0. Because in the U equations, it occurs in both terms. Right, so you have U plus the product of all the curves that intersect. X is equal to 1. If a curve intersects itself, it shows up in both terms of the equation, so you cannot set it to 0. So that means that all of the self-intersecting curves are irrelevant for the field theory limit. Okay? If you want to take these curves and see what they look like in the field theory limit, you can just throw all of them out. That's the beginning of seeing the sense in which we have a bigger world of objects that kind of connects to string theory in some limit, but is not necessarily string theory. Because it turns out that string amplitudes require you to put in every single curve on the surface, including all the self-intersecting ones. Okay? And that's why, you know, if someone handed you a one-loop string amplitude and said, please take the field theory limit, you'd be a little terrified of doing it because of these horrible Jacobi theta functions everywhere. What are you supposed to do? Where are those coming from? They're coming from the product of these infinitely many self-intersecting curves. They're literally irrelevant baggage as far as the field theory limit is concerned, so you do not need them. Okay? So when you ask the question, what do you include, it's a little bit up to you what you want to do. Okay? But if I'm strictly talking about the field theory limit, the answer is a little bit more interesting, and it's related to something I just want to say about these U variables now. And then I'm just going to answer this question, but it dovetails exactly with what I was going to say. So I have these U variables that depend on the Y's for any X. Let's once again, some yk. Let's once again put yk equals e to the minus tk, just so I can talk about tropicalization. So again, we're interested now in what happens when the sort of t goes to infinity. You know, what's going on as we go to infinity. And so u is going to go to e to the something, e to the, we'll call it alpha, times the sort of tropicalization of ux. Okay, that's, e to the trop of ux, and this I'm going to call e to the alpha x. Okay, so now alpha x is going to be some piecewise linear function on t space. Now, the properties of the u's guarantee the following. So the sort of key point about tropicalization and these alpha variables is that these alphas are the global Schwinger parameters. And so the key point is that if I take alpha for a curve x, it's a function on this space where all these cones live, right? In this t space. If I take alpha for curve x, and I evaluate it on the g vector for the curve y, it's equal to 0 if y is not equal to x, and otherwise 1 if y equals x. Okay, so the tropicalization of the u variables lights up the g vector, okay, for its own variable and is 0 on everybody else. Okay? And that's why, if you then just write down this integral, you know, dnt, whatever the dimensionality is, e to the minus the sum over all the curves on the surface, the x, I'm sorry I'm doing, maybe I should say the sum over all curves c. The x associated with the c. Remember, with every curve, we just figured out how to associate the momentum. I can square that momentum to get an x. Or I could just say that there's variables xc associated with every curve. That's my kinematics. My kinematics space is some variables xc associated with every curve, multiplied by the alpha associated with that curve. Okay? This is something which looks like Schwinger parameterization in every cone. Okay? And this is something which is equal to the sum over all the cones, the product of the 1 over of the x little c for this for the c's belonging to the cones, okay? Which is what we call the amplitude before. Right? So now this brings me back to your question. Okay, so if we're doing this before doing loop integration, all of these x's have the loop variables in them. We would have all these infinitely many winding guys, right? And that's fine. Okay, I do the loop integration. This is in Schwinger form, so I know what I get. I get semantic polynomials. Except these you would call surface semantic polynomials. They're not semantic polynomials for a fixed graph. They're the semantic polynomials associated with the entire surface. Okay? So there's an analog semantic polynomials that would put all the curves on the surface together. They're the same old polynomials, very similar to the polynomials that you had before, except with these alpha c's showing up. Okay? And now you have something which is mapping class group invariant, so you have to mod up by the mapping class group. You mod up by the mapping class group by putting a little extra factor of a kernel in this measure that does, again, to a physicist, the Fedorov-Popov trick for modeling out by symmetries. Okay? There's a very standard and simple way of producing this kernel. You can do it for all surfaces at once. It's algorithmic. You can put it on the computer and do it to 10 loops. It's all fine. Okay? So these formulas are absolutely concrete. There's nothing formal about them. You can put them on the computer and integrate. Okay, so Giulio Salvatore has put them on the computers and integrated them to 10 loops. Okay, so there's no issue. You know, say there's an I epsilon here, rotate there. Just of course, if the kinematics is positive, Euclidean, et cetera, once the kinematics gets interested in all the usual physical issues about thresholds and I epsilon, those of course don't disappear. But I just want to stress this is not some sort of formal object. In the regime where the integral looks well defined, it's 100% well defined. But now coming back to your question, you see, the purpose, so what I'm supposed to do in general after I loop integrate is put this kernel there. The purpose of the kernel is to sort of kill the faraway windings. Okay? So that's effectively what it does.
Can you say a little bit more about the kernel?
Yes.
I don't wake up every morning and think about Mirza-Khan.
No, I know. I'm sorry. Yeah. So let me instead of saying, let me say it in a simpler. Let me say what it is in a simpler example. So, and this is really all that's going on, but we can see it already in this example. Let's say you have a function of just one variable. Let's say you have an f of x, which is translationally invariant by some amount a. So it's equal to f of x plus a. Okay? But what you like to do is make sense of integral minus infinity to infinity dx f of x. Okay? This is, of course, infinite. Exactly because it's translationally invariant. Okay, so there are these translations t. So this is equal to infinity. And so what's our usual attitude about this? Our usual attitude, if you're if you're in high school student or undergrad or something, is to find a fundamental domain, right? So in this case, fundamental domain would be a little interval that starts at b's, any old b, and goes to b plus a. Okay? And so what you say, really what I should do is I want to make sense of integral dx f of x mod translations, whatever this means, mod translations, okay? But what this should mean is just the integral from b to b plus a dx of f of x. Okay, so this is the fundamental domain idea. All right? And you can try to do that for surfaces too. Just the mapping class group gets more and more complicated. This is not a fun problem to try to identify a fundamental domain. You can do it for a torus, you know, but things get, I mean, already for a torus, SL2Z is not, you know, a walk in the park. It's not that hard, but it's not the most trivial thing either. And then it gets more and more complicated from there. Okay. All right, but the sort of Fedorov Popov, or but physicists run into this issue all the time, right? Whenever you define any path integral in a gauge theory, it's infinite because it's gauge invariant, and the volume of the gauge group is infinite. So we have to figure out how to mod out by these kind of symmetries all the time. And when we do the path integral gauge theory, we absolutely do not do this. We don't find the analog of the fundamental domain, which is insanely complicated. Right? That's a sort of space of all possible gauge invariant states. It's ridiculously complicated. You'd never think of doing that. Instead, you judiciously insert 1. Okay? So what you do is you say, I'm going to just pick any old function. In this case, I'm going to pick any old function g of x. Okay? Let me pick some g of x. I'm going to draw g of x. Here's g of x. And g of x is going to look like this. Any old random g of x you like. Okay? Okay, but I'm now going to insert 1 is equal to the sum over all k of g of x plus ka, just translating g, divided by the sum over all k, g of x plus ka. So clearly I haven't done anything. Okay, and I'm just taking a function and all of its translates. Okay? So far so good, right? So I'm going to insert that into my integral. My integral is integral minus infinity to infinity dx to begin with 1, but I want to somehow mod out by the translations. Okay? 1 times f of x, but the 1 I'm going to write as a sum over k, g of x plus ka, over, I'm going to call this big sum g. Let me call this big sum capital G. Okay? Capital G. The only thing I need is that capital G does not vanish anywhere. Okay? So I want this formula to be meaningful. So capital G had better not vanish anywhere. So G of x had better be kind of like enough non-zero so that when I translate it, it can itself even vanish in a lot of places. Like G of x could even look like this. And G of x could look like this so long as this length is bigger than a. Okay, so that when you translate it, the translates sum together never go to 0 anywhere. Okay? So I just want this denominator to be well defined. And then it's sort of, times f of x. And then it's sort of obvious what's happening. Because precisely by translational invariance, in every term of this sum, I could translate back to k equals 0 if you like. Okay, so modding out by the, so if there was a fundamental domain, even without finding it, I know that, that this is going to be the same as the integral minus infinity to infinity, just one term here. For example, just g of x divided by capital G times f of x. Okay. If you like, all the other ones are just copies of this one by the action of the mapping class group, and modding out precisely throws them out. Okay. Now, this is very cool. Of course, if you make a choice for g of x to be a step right with size length x, a, this goes back to the fundamental domain picture. Okay? You can put g anywhere you want, and this goes back to the fundamental domain picture because the sum of the g's is just equal to 1. But you don't have to be smart to do that. Just choose a random g, any g that you like. It's a little fun to do it with, with a Gaussian or something. It's slightly surprising that this integral over everywhere without thinking gives you the right answer, but of course it's designed to do that. Okay, so this is what physicists call the Faddeev pop-up trick. Perhaps it's not being dignified with that. I'm sure
this is your way
Euler did it in the 1700s.
This is your way of taking a quotient.
This is a way of taking a quotient. This is a practical way of taking a quotient without manifestly identifying a fundamental domain. Okay, that's the sort of key point.
Can I follow up with
absolutely? Yes.
One more question.
Yes.
Only one.
Yes.
Not two. Okay, so I'm gonna ask the what's in it for me question.
Yes, yes.
And it's as follows. In this institute, there's a geometry group.
Yes.
And there's an algebra group.
Yes.
So now you moved, everything into the geometry sense of Teichmüller space and
or the algebra
and Riemann's. I would like to take something back to the study of algebraic curves.
Yes, yes.
So the moduli space MG or MGN.
Yes, yes.
And I'm interested in algebraic curves.
Yes, yes.
Not in Riemann surfaces. So how can I make use of this technology to study algebraic curves?
I don't know. What I would say is that what makes it useful for us is in fact it's distinctly algebraic flavor. Right? I mean that's the point. You just have these algebraic equations. You solve as ratios of polynomials. And this does something. It gives an algebraic way of characterizing.
But the algebra is on the geometric analytic side, right?
Sorry.
We have to somehow cross the transcendental divide. I mean, you spoke about ugly Jacobi theta functions.
Yes, right.
They seem nicer than.
Yes. Well,
so we have to somehow go from the analytic side to the algebraic side.
Yeah.
And maybe this gives. I'm willing to do numerical computations, even with Giulio.
Right. Well. Maybe one interesting point to make is also related to your earlier questions about the infinitely many U's. So you can ask, I mean, we know that if we're talking about string theory at loop level, there are Jacobi theta functions everywhere. Where do the Jacobi theta functions come from in this world?
For example.
The Jacobi theta functions come from the product over infinitely many curves. Okay, so that of course the product representation for a Dedekind eta or Jacobi theta is like product of 1 minus y to the k, right? What are those product 1 minus y to the k? In this language, the 1 minus y to the k is coming from these f polynomials. And there's infinitely many terms of the product because we have infinitely many self-intersecting curves. So that's, maybe at least one thing that I find interesting is that a lot of this story can be abstracted away from curves on surfaces. There's even more general settings where you can have associated both with cluster algebras and quiver representation theory and so on and so forth. There's more general settings where you can associate all of these things. There's sets of variables and U variables that go along with them. They satisfy U equations. There's infinitely many of them and so on. And so it's natural to wonder whether the things like Jacobi theta functions that are associated with surfaces have similar generalizations in these bigger settings. It's somewhat, for example, maybe just to say a negative, if I give you a Jacobi theta function, the most exciting thing about it is its modular properties. And so you can ask, are its modular properties obvious in this way of writing things? Absolutely not, as far as I can see. What this tells you is that it's good to write the formula product of 1 minus y to the k. That comes out of this sort of way of thinking.
But we should see this, using the U equation formalism, we should see Riemann theta functions and all that.
Yes, absolutely. Absolutely, yes.
And it could be a tool. It could be a tool to study and evaluate.
It could be, and I think one really key thing, which has come up in the question I also haven't answered yet, is it gives a natural regularization of these things. Okay, so that's kind of the point. If you're a string theorist talking about calculations at high loop order, there's some Green's function on a surface that you have to compute. You compute it roughly by the method of images. It involves infinite products that have to be regulated. They're very subtle things. When they come out in the U form, they don't have to be regulated because they're manifestly finite products of things that are bounded between 0 and 1. So, and it gives you a picture of what's regulating it. The sort of degree of complexity of the curves that you're talking about is what is regulating it. So I think that connection, probably the most useful thing about it is a way to sneak up on these very infinite objects in a well-defined, finite way that has geometric meaning, right? In terms of putting these cutoffs on the complexity of the word and on how complicated the curve looks on the surface. And finally, coming back to your question, you see, this now means, so what was the purpose of the g of x? The purpose is kind of mostly to shut off a little bit away from A, right? So now, of course, when we do this in our setting of the math class, we don't choose random g of x's. We choose the g of x's to be made exactly out of these alphas, right? So it's very easy to build, sums of alphas whose translates are never zero anywhere that you can put in the denominator, right? That means that in this formula, in the numerator, you're just going to have the alphas for some finite set of curves. Because there's a finite set of curves upstairs, there's literally a finite region in this fan in which this kernel is non-zero. Okay? And so you don't need to keep infinitely many curves. You only have to keep a few curves, the curves that are non-zero in that neighborhood. Okay? So that makes it, that's what really allows it to be completely practical, because I told Bern that these u variables mostly go to 1, or if you tropicalize them, only in very narrow cones far away do they matter. But in a precise sense, you can throw them out if you're doing the field theory computations when you mod out by the mapping class group, because they are literally, you don't go there. Okay? It's just that a fundamental domain is a lowbrow way of saying it is choosing one representative set of Feynman diagrams. Like you choose one representative set of diagrams to cover the space. If you do that, that's going to look very ugly. Right? Means you have a weird collection of cones that you say, okay, this collection and their translates are going to cover the space, but you have to artisanally choose the collection of cones. Instead of doing that, you just sort of light up some region by this method. Okay, so here's some sort of wedge, and that's what I shove upstairs. And then I'm done by this idea. So long as I just do the integral over that cone, it's gonna pick a third of a Feynman diagram from this cone and 2/3 of one from the other cone. I'm gonna add them up in some nice way, but without thinking, I cover the entire space. And then it's finite. Then it's really a finite number. Yes.
I know you stated the third commandment that it's forbidden to ask the third question.
Yes.
I will cross this forbidden
yes.
things. Okay, so it seems that you are trying to go back and forth in this cross-pollination between mathematics and physics to this problem. It's normal. You got the kicks with abstraction. One natural question. Which arises, I think. Are there any toy models in 3 dimensions with the same formalism? Of course, without the monstrosity of the professor on the right top.
I will stop you there and say this is already a toy model. It's already a toy model that actually is dimension agnostic. It could be in 3 dimensions if you wanted. That's I never said what the dimensionality was in this story.
Yeah, so you're saying that there's a natural generalization between
generalization or specialization. That's there's the number d. It doesn't have to be an integer. It could be complex. It could be anything you want. But that's one of the nice things about working with the scalars. As I mentioned yesterday, although I won't have time to explain it in detail, it is surprising that starting with this formula just for scalars, secretly it knows about gluons as well. Okay? So there's a way in which it knows about gluons and pions, also in any number of dimensions. So that adds a lot of physical excitement and novelty about these ideas.
So you're saying,
but nowhere here do we say anything about the number of space-time dimensions.
Your Professor Arkani, you're saying that the generalization is completely obvious, and you have only 3 matrices, for example, for R3.
Oh, no. That 3 has nothing to do with it. In any number of space-time dimensions, you always have the same 2x2 matrices. If you're asking if there's a generalization where you have, instead of words, I don't know, some 3-dimensional words, and you'd multiply 3x3 matrices and 2x2 matrices, I have no idea. Probably there is, because mathematicians are very interesting people who invent all kinds of things. But anyway. I think we have to stop now for the break, right? For the tea break? Anyway, so what I can do with the time that I have is give you what I mentioned in the beginning is the sort of one very new application of the ideas that we've just been talking about. That gives us access to a very interesting region of physical processes involving scattering with asymptotically large number of particles. So we're going to again talk about this trace phi cube theory, but I want to imagine I have amplitudes. Oh, this is a nice drawing in trace phi cube, but where I have sort of n particles, and n goes to infinity. Okay. And I want to say something about what these amplitudes look like. Now, again, I'll just say this. I said it already before as part of the motivation. What I like about this question is it forces you to think. It makes it very clear what part of what we're doing before is continuously connected to standard ways of doing physics and what could be really new. Because none of the ways we think about computing amplitudes, whether we interpret amplitudes as canonical forms or BCFW or other kinds of recursion relations, every one of these pictures has something recursive built into it, right? A canonical form is an object that recurses to a canonical form, right? You build up higher point amplitudes by gluing together lower ones, right? So it's all a picture that the simplicity is in few particles and complexity is in many, okay? And so we're looking for something essentially new, where there's simplicity when the number of particles is huge. So that's what we're looking for, okay? And the clue that such a thing is possible is from the tropical representation of the trace phi cubed amplitudes that I now want to write on this board, okay? So if I look at the tree amplitudes for trace phi cubed for n, then I can write it as this integral dn minus 3t e to the minus some s, okay? That depends on t. And s of t, this is now associated with this picture of the mesh, okay? So s of t is the sum of x1j, t1j. Okay, so these t's are associated with this bottom boundary. Okay, so this is the mesh. We mentioned it. I mentioned it before, but that's associated with this kind of triangulation, where that's 1, 2, 3, 4. Right? Okay, so so again, this is just a picture as a mnemonic for thinking about all the variables in the problem that makes it easy to write this expression. And then you have, for every internal C, you have a sum of these internal C's. So the internal ij's, Cij times something. It's a max of 0 and a bunch of things, right? And so let me just give it concretely in this example. I hate it when people write formulas with bounds on indices that you can barely read on the sum. Okay, so I'm not going to do that. So I'll just sort of show what it looks like in a big enough example where you can see how it generalizes. Okay, so if I have this example, that's 1, 3, 1, 4, 1, 5. Okay, so my action is T13 is T13 x13 plus T14 x14 plus T15 x15. Okay, and then associated with this C, so this is C13, I have plus C13 max of 0 and minus T13. Okay. So in Carolina's language, remember this was associated with that little Minkowski sum in that direction. This guy's the other direction, this guy's the other direction. So there's C13, this would be 2, 4, 2, 5, 2, 6, 3, 5, 3, 6, and 4, 6. Okay, so then I'd have plus, so I'm going up this way, also because organizing about how complicated these things are. So plus C24 max of 0 and minus T14, plus C35 max 0 and minus T15. And then here and here I have plus C14 max of 0. You see I've gone up to 1,4 here. Okay? So it's max of minus T14 and minus T14 minus T13. Okay? So I go as far up as I go, and I go down from there to see it's a max of all of those guys. Okay? So this guy instead would be plus C25 max of 0 and minus T15 minus T15 minus T14. Okay, and finally this one would be plus C15 max of 0 minus T15 minus T15 minus T14 minus T15 minus T14 minus T14. By the way, I apologize if these things all have minus signs on them. You might have thought it would be convenient to just reverse all sign conventions and call all these things plus signs. If you thought that, you would agree with all my collaborators. And so in the papers, you'll find it in that officially intelligent way. But I have my own personal reasons for preferring it this way. So screw you all. All right? And that's a technical term for my collaborators. Okay, so anyway, so what again? And so I hope the pattern for any n is clear, right? You're going to get a max of 0 on these strings of sums of negative t's. Okay. So once again, in this example, already we see we have 1, 2, 3, 4, 5, 6. We have 6 little tropical functions that are going to turn this 3-dimensional space into 14 cones, right? So here we have 14 diagrams at 6 points as Catalan numbers. We have 14 diagrams. And so we're starting to see the point, right? That as we go to large n, there's n squared roughly of these maxes. They have order n terms each, and magically their domains of linearity turn into all the roughly 4 to the n diagrams at large n. Okay? So that's why there's some sort of vague hope that maybe this integral, it's a single integral. I'm not talking about summing diagrams. It's a single integral. It's a single integral made out of like simple objects that if you sort of squint, even maybe have some kind of seeming nice continuum limit, right? These sums of consecutive t's, maybe they look like an integral. You go to large n, you replace sums with integrals, or that integral kind of turns into a path integral. There's all sorts of sort of vague words that you could say about why you expect something nice to happen here in the large n limit. Okay? That's exactly what we're going to see. But I first want to do 2 things here. First, I want to be a little bit more precise about what a large n limit could mean. Because when you take a limit, you always have to say what you're holding fixed. Okay, so we have to hold something fixed as we go to infinity. And then I want to do the super simplest case of a large n limit, just to give us an idea of what we're looking for. Okay? So the first comment is, what are we holding fixed in the large n limit? Okay? What's fixed? So large n kinematics, essentially, I want to talk about. And if you're a physicist, we could actually spend a fair amount of time on this topic. It's actually interesting to talk about. But let me sort of give you a quick impression, then I'll make a very, very precise statement. So if you're a physicist, you'll care about the physical implications of all these things, but we can just sort of make the precise statement quickly. So remember, we said that we started with this picture where we imagined, we have momenta of particles that we put end to end to make this momentum polygon, to give us this picture of momentum conservation. Okay. So this picture immediately, so as n goes to infinity, you have to somehow give me a large number of momenta, right? But in some way that something is held fixed. So the obvious thing to do here is to say that what's held fixed is just this curve. I draw some curve. Okay? I draw some curve C. And then for any finite n, well, I just plonk down n points on this curve. Of course, maybe I plonk them down with some density. There's more details we could talk about how I plonk them down. But at 0th order, I'm just going to plonk down a bunch of points on this curve. And I'm going to use that to define my momentum polygon. Okay? So this defines my momentum polygon for any finite n. Okay, so at least here we've defined something, right? Here we've defined something that is going to stay fixed as n goes to infinity. And so that's what we want to know. We're going to have the amplitude is going to depend on these n momenta. But the hope is, again, this is sort of vague, that at large n, the amplitude will only depend on this curve C. And it won't depend on the particular way that you put points on it. Okay? That's what we want to see. If it's true, something like that is true. Now, that picture immediately translates to a kind of an obvious state of the language of this mesh. If we think about this mesh as defining our kinematic space, don't worry, I'm going to write down a simpler version of this equation again, if you're missing it. Is that, so another way, so kinematic limit 2, another way of talking about it, slightly more general way of talking about it, is draw this mesh, okay? But now just imagine that the x, so my kinematic variables are some xij's in here, right? So, and I'm just going to imagine this is a very fine mesh, okay? So I'm going to imagine that the xij's on the inside are really secretly some smooth function. I'll call it x of u and v, but when, for example, u is I over n and v is j over n. Okay? So it's like, here is u, it goes from 0 to 1. Here is v, it goes from 0 to 1. The other way, I don't know, right? So I have a smooth function of x of u and v inside this triangle, and I'm just discretizing, I'm just plonking down a mesh and reading off the xij's from the value of that smooth function evaluated on the discrete points. It doesn't have to be a uniform mesh. We can do it in many ways. So this is the sort of slightly more general picture. I mean, obviously, everything that looks like that will give me something smooth in here. Okay? But now we're just going to say it in here. I'm just going to have a smooth x inside this. Triangle. Okay, is that clear? So once again, the hope now is that the amplitude as n goes to infinity is now just going to become a function of this smooth x of u and v. Okay? Okay, now let's get a
Can you
slightly
say
more.
one more time how I compute the x from the c?
Oh, I'm sorry, yeah, the x's
there's
are,
some
yeah, I give this curve.
Some integral, no, but suppose I have a continuous curve.
Yes.
And I want to compute the continuous x.
Yes,
I'm
that's
willing
right.
to do a continuous computation.
Yes, a continuous computation. I pick a point here to call 0. Okay, so my curve is labeled by some little x that depends on a parameter. Let's call it u. That goes from 0 to 1. So here is u equals 0, u equals a half, u comes back to 1 here. Okay. And so my x of u and v, the sort of first guess for x of u and v would be little x of u minus little x of v squared. Okay? And for the particle has a mass plus m squared. Okay? Okay. So that's what we're talking about.
Also like the limit and the infinity on the smooth curve? Or?
Yeah.
Oh, okay.
Yeah, that's the point. That's how I'm defining the limit. Okay.
Is there some notion of some shellness in the curve, like the d squared equals?
You could ask for that or not. Okay, and actually, so this gets into the longer physics discussion. You could ask for that or not. The simplest thing to do is just say these are whatever they are. You would call this an off-shell correlator. The formulas are exactly the same. You could interpret it as an on-shell amplitude with a little bit of scaffolding on top of these guys if you wanted. Okay, so and that's where there's about a 45-minute discussion of all the different ways we could draw this curve. There could be space-like, there could be time-like. They have interpretation of a bomb going off. They have the interpretation of lots of particles going in, lots of particles going out. So there's lots of different sort of physics words.
But then there was also the c.
Right.
So the c is the Hessian of x?
We're going to come to the c's in a moment. That's going to be the sort of key thing that makes that gives some hope that something simple is going on. Okay. Okay, but in fact, so before getting there, I want to do the very simplest version of a smooth x, which is all x's equal. Okay, so that's the very simplest thing we can do. What if all the x's are equal? Okay, let me put it here. So if all x's are equal, Then the amplitude is very simple. What is the amplitude? Well, every single finely diagram, every diagram is the same. It's like 1 over x to the power of the number of propagators, right? So all the x's are the same. So the amplitude is just 1 over x to the n minus 3 multiplied by the number of diagrams. The number of diagrams are the Catalan numbers. And it's very easy to see that the Catalan numbers grow like 4 to the n at large n. So we said that already. So already here we see that this goes like 4 over x to the n at large n. Okay. So that's our sort of first more precise hint for what we're looking for. And if you're a physicist, you're very excited to see that n in the exponent. Okay? Because the amplitude looks like e to the n times some function a of x. In this case, a of x is just log 4 over x. Okay. Or I put a minus sign there, and it would be log of x over 4. Either way. Okay. But it's very common in physics when you have a small coupling in a theory that the leading amplitude or partition function or whatever looks like e to the minus some coupling, normally we call it 1 over g squared, times the thing that sits here is controlled by some classical physics. That's the leading thing. This is called the leading classical behavior. And then you do a semi-classical expansion around it, and so on and so forth. But the sort of, for example, in the path integral, in the finest path integral, we have e to the 1 over h bar. It's Planck's constant that goes downstairs in the action. Okay. So
in some
yes,
sense, this
correct.
equal 1 is a complicated case, because
Yes.
the dimensionality of your curve also goes up. Right?
Sorry?
Should I think about your polygon staying in so your curve being in a fixed dimension?
You can think of it as saying in a fixed
But
dimension.
this is not a good model.
That's
for
right.
it.
This is
That's-
not a good.
It's a bad model for
It's a
that.
bad model for that. Exactly. So this is the slightly longer discussion about exactly what does or doesn't work for the story that I'm telling you. Just to skip to the end, the story that I'm telling you is valid for a fixed curve and fixed dimension. But you're right. X equals 1 is not a model for that because we cannot realize x equals 1 from any curve in a fixed number of dimensions. Absolutely. Okay? But somehow, it's kind of interesting in this entire story, everything is about the x's. In our stories, everything is about the x's. That's sort of the whole point. The momenta are somehow far away somewhere, right? Everything is about the x's, so it's natural to ask this question in our story, just to get some sort of first handle on what's going on. But I want to stress that this is now looking exciting, because it looks like at large n we should be looking for some kind of theory whose weak coupling is 1 over n. Exactly, right? 1 over g squared to the n, so n is 1 over g squared. So it looks like there's a dual theory at large n. Okay, so if you're a physicist, those were in the beginning of any talk on the subject, you would say this is evidence for some kind of dual theory at large n. We're going to be finding this dual theory at large n. That's exactly what we're looking for. Okay, so, but of course, as Bernd was saying, that's a very, very special case. Let's imagine more general x of u and v. And now comes a second interesting point. Maybe before we get into this a second point, let's go back to this picture. This is actually essentially repeating slightly more slowly something Carolina was saying at the end of her talk yesterday. Let's say we have this, this example at 6 points again. Sorry for the bad drawing. And it's just kind of interesting. So the whole associahedron, or the whole amplitude in our language, involves turning on all of these C's. Okay? But let's just see what happens if we turn some of them off. Okay? Carolina mentioned that there are some limits where we turn so many off that the associahedron collapses the dimension and the amplitude gives us a 0. But let's just back up a little and see what some other sort of simple things look like. One simple thing you can do, remember these guys were intervals, right? Whatever direction that was, right? So one kind of obvious thing to do is just turn off all of these guys and just have these intervals. Then the object is really simple. It's a hypercube. Just a cube in this case, right? And also the amplitude is extremely simple in that limit. Okay, so if you remember, Now I erase the action, but let me write it again. You know, these contributions, so my action was T13 x13 plus T14 x14 plus T15 x15. Remember, I'm integrating, the amplitude is integral dnt e to the minus s. Okay? So in this example, this is s, it has these linear pieces, and then these guys with a simple things whose maxes only involve one variable at a time. So C13, max of 0 and minus x13, plus C14, max of 0 minus x14. Sorry, C24 plus C35, max of 0 and minus x15. And a t. Thank you. Okay? So these integrals are really simple too. It's just, you know, a single integral, right? So what is that integral? What is this action? This s, like when t is positive, when t13 is positive, it's equal to t13 x13. And when t13 is negative, that's the max. So here it's equal to this slope. So this is c13 minus x13. Sorry, this is times minus t13. Okay? So just as a slope of different slopes, I made them look the same, but different slopes on this side and that side. And so when I do the integral from that, I get 1 over x13 from the integral from 0 to infinity. And from this side, I get plus 1 over c13 minus x13. Okay? And so I just get a product of those factors for each one of these things. So times 1 over x24 plus 1 over c24 minus x14, 1 over x14, sorry, x15 plus 1 over c35 minus x15. So I just get a product of these factors. And that's just, each one of these is the canonical form for that little interval, or it looks like a 4-particle amplitude, just a little local 4-particle amplitude. Okay? So this is a limit. This is something Nick loves. They're called the maximally split limit. Okay, so where the amplitudes are maximally split. Byrne loves, because this is a kinematics for which the saddle point equations, the scattering equations is precisely one solution. All sorts of nice things about this limit. So we call them maximal splits. And the association is just a cube in this case, right? Of course, the association in general is much more complicated than a cube. However, the essential story you're going to see is that in the large N limit, the association essentially turns into a cube in some particular specific sense of that statement. Okay, so, all right. But anyway, let's keep going here. There's another obvious thing that we could do. We could turn everyone off here and turn this guy on in the corner. Right? That's also a limit where we get a non-zero amplitude that's as simple as possible, and I won't write down a formula, but it's just it's just the canonical form of that little triangle. Okay, it's a single term again. Okay? So if I turn on all of these guys, I get something simple. If I turn on that guy, I get something simple. Okay? I add up everything, I get the full associahedron. It's actually amusing that if you take this simple guy and that simple guy, so this gives you a cube. That just gives you a top dimensional simplex. Already just summing those guys is a very complicated object. Okay? It's almost as complicated as the full associahedron in this case. It just shrinks 2 of the edges of the associahedron. Okay, so you have 19 edges instead of 21 for the 3-dimensional associahedron. It has all the same facets it had before. Okay. So it's already a pretty rich object where you Minkowski sum just the little intervals on one side and the big top dimensional simplex on the other side. As you go to large N, this object has roughly 2 to the n facets. It has a lot of facets. Okay? It's quite complicated object. Sorry, it has a lot of vertices. It's 2 to the n.
But the dimension always goes up, right?
The dimension always goes up. That's right. Exactly.
So there's no scenario where the dimension stays the same.
No, exactly. So so I gave you the reasons to expect a large N limit at the very beginning before. The reason to be worried is that the integrals are not staying in fixed dimensions. So the integrals are sort of getting bigger and bigger. And so it's not obvious from that point of view that a large n limit should exist. Okay? But here we're not talking about large n, I'm just saying something in general. If you take a big mesh, there's two limits where it's extremely simple. One where you just turn on the sum ends on the strip on the left, one where you turn on the sum end in the corner. In one case you get a big cube, in the other case you get a simplex. Already when you just sum these two guys, you get something really complicated. Okay? Just summing these two guys is something pretty complicated. Of course, the whole association is summing everything else. Okay, so already these guys have roughly 2 to the n vertices. If you put everything else in there, you grow to roughly all the 4 to the n vertices of a full association. All right. Now let's return to large n and to Bernd's question about what the C's look like, because that's the sort of key, that's one key thing. So this is a pretty large n, and here's the cool point. So I'm imagining that my x's are, somewhere in the neighborhood of this, all the x's equals constant. They're not equal to a constant, but they're all, they're varying. They may be varying a lot, but they're staying away from 0. Okay, they're sort of staying away from 0, but they're varying a lot inside this triangle. But that means something really cool. Let's look at the x, the typical x on the inside. As Caroline said, typical x on the inside is this xij plus xi plus 1j plus 1 minus xi plus 1j minus xij plus 1. This is roughly the derivative in I, the derivative in j of x, the discrete derivative of I, the discrete derivative in j of x. And therefore, this is of order 1 over n squared. Okay? All right? This is of order 1 over n squared. I should have said, it's really 1 over n derivative with respect to u, 1 over n derivative with respect to v. Okay? So this is something of order 1 over n squared. So all the c's on the inside are small. Of course, there's many of them. Okay, so this doesn't mean that you can just throw them out. Okay? But it kind of means that the c's on the inside are tiny. Meanwhile, what are the c's on these corners? These are x plus x minus x, but this one is absent for them. Okay? So the c's on these corners are of order 1. These guys are all of order 1. And this guy on this corner is also of order 1. Okay? So in this continuum limit, when the x's inside are taken to be smooth, then the c's on the outside here and this one here are of order 1. And all the ones on the inside are of order 1 over n squared.
Sorry, Nima.
Yes.
This I don't understand why they are order 1. So the other one you interpreted as some derivative?
Yes.
Okay, here one of them is missing.
Yes.
That I understand. You can't write it as a double derivative
Yes.
anymore. But what can you write it as?
Oh, you can't. It's just x plus x minus x. All these x's are of order 1. So this is of order 1.
Oh, it's like a single derivative plus something like
Well, it's like a single derivative plus an x.
Yes,
Okay?
it's like
If you like, it's just x minus x plus an x. This is of order 1. I want to stress something. So if you thought that the x should go to 0 on the boundaries, then this would not be true. Okay, so this is sort of important that in this story, again, this is the half hour if you're a physicist, that we added this mass squared. Okay, we add this m squared. So even on the boundaries, it's not going to 0; it's going to m squared. Okay, that's what makes it happen. But on the inside, all the m squareds cancel. On the outside, they don't. Okay, so.
Just to be more specific,
Yes.
one x of order 1 and one derivative of order 1 over n.
That's right. So the whole thing is of order 1 over n. That's right. This is order 1 plus order 1 over n, but you can figure it out. Okay. So that's already some indication. So let's for the moment forget about all the internal c's. Okay. As I said, we won't actually forget about them. We're going to put them all back in a bit. But this at least suggests that it's an okay idea to start thinking by throwing out the c's. And it's interesting that that exactly lands us on this sort of first complicated associahedron. Okay? It can be super simple when it's just these guys on one end. It's super simple when you just turn on the guys on the other end. You add the two of them, you get something complicated at all. Anyway, somehow that first complicated thing is our first object of study here for a natural reason. All right, and that lets me write the integral down. I can now just write a single integral down that we can all stare at. So I'm just going to introduce some.
So Nima, since you mentioned the scattering equation, should we solve them for these two at the inside and outside? And
yeah, well, as you see, this large n story suggests a dramatic simplification in solving the scattering equations at large n.
For this situation.
For all situations. For all situations in this world, even when we turn back on the C's. Okay? So that's so all of these things go together. I'm actually talking about what's sort of physically more interesting, perhaps, about what the field theory amplitudes look like. We're a lot more tropical words, and it's actually much more interesting and involved analysis. But the same statements end up being true for string amplitudes in the limit where the energies are huge, where you're just solving the scattering equations, and the arguments are one-line arguments for what the large n results look like. So they're much simpler at large n. There's a specific sense in which you isolate a single solution, it's rational, and you follow it, and it becomes simpler and simpler as you go to a large n. And you'll see there's sort of one simple idea, which we probably won't get to it from the strings, but once you see what it is here, you'll immediately see what you have to do in the scattering equation context. Okay.
Nima?
Yes.
So what is the statement about the middle one, since there are many of them?
Yes.
Is it that they individually contribute in different regions, or?
No, I mean, at the moment, you have no reason to ignore them, okay? At the moment, there's 1 over n squared, but there's n squared of them, so you can shrug, okay? You can at least say they're definitely not more important somehow. They're not going to, like, dominate everything. So, and as we'll see, we might see if we, I think we might even see. You can really include their effects. Sometimes they're not important, sometimes they're important, but there's going to be a formula at large n in all regions of the kinematic space that you care about, where you can see all these things happen. All right, so okay, so what is so let's turn off the C internals. And so our amplitude is then just the integral dt13 up to dt1 n minus 1, from minus infinity to infinity, e to the minus s. S is the sum of t1j x1j, the sum over j, plus the sum over j c j minus 2j. These are these corner j's times the max of 0 and minus t1j. And then has one complicated term, which is this corner c, c1 n minus 1. So these are the c j minus 2j, and this one c here is c1 n minus 1. Okay? c1 n minus 1, and this one has the max of everybody. So max of negative t1 n minus 1, t1 n minus 1 t1 n minus 2, and so on. Okay? So we have to do this single integral. I'm going to introduce a little bit of notation, just so I don't drag these things around all the time. So remember, obviously there's a simplest part of this action. These first two terms, those are the ones that gave us the hypercube. Those are the ones that were sort of trivial. I'm going to call this S naught for the moment, and I'm going to call this S1. And furthermore, in here, remember what it looked like. In here, when t1j was positive, it had a slope that was x1j. When it was negative, it had a slope that was cj minus 2j minus x1j. So I'm just going to call this one aj and this bj. Okay, they just stand for those variables. And I'm going to call c1 n minus 1, I'm going to call c. Okay, so I don't just keep dragging these indices around. So my amplitude depends on the aj, the bj, and the c. Okay, that's what the amplitude depends on. Okay, and so I can write this as an integral. Let me write it in this way, as an integral, again, dt13 up to t1 n minus 1. And I'll write as a product over j, these sort of independent things. Okay, so I'm going to write this as a product over j. Slightly suggestively, I'll write them as p hat of tj. And then an e to the minus s1. Okay, where p hat of t, p hat j of t1j is e to the minus ajt when t is positive, and e to the bjt when t is negative. Right? That's just exactly the thing that we're talking about. Okay? So that's our integral. Okay, so once again, in the limit where the c is 0, if I set c to 0, I know what this is. It's just the product of 1 over aj plus 1 over bj. Right? So in that limit, the answer is a simple. C is this complicated term, right? C is the complicated term where all the variables talk to each other. Everything else, they're decoupled. All right. So, and again, if we officially do this integral, the way to do it is to find the regions where it's piecewise linear, and then we're back to doing the diagrams, right? That's just back to where it came from. So we have to figure out some way of thinking about this integral, which is not that. Okay? So, one key idea, it's just psychology, is to interpret this as saying, well, okay, well, at least there's a limit where the answer looks simple. So I'm going to define A naught to be the product over j of 1 over aj plus 1 over bj. This is exactly what I would get. This is what the amplitude would be if the c was 0. Okay, this is aj and bj as I send c to 0. Okay? So it's sort of reasonable to look at what a is relative to a naught. Okay? So if I look at a divided by a naught, well, a divided by a naught has a very nice interpretation. A divided by a naught has the interpretation of an expectation value of the quantity e to the minus s1 in the probability distribution given by e to the minus s naught. Right? Where now what I mean by the probability is there's an independent probability for every t. They're all independent. And p of t, not p hat of t, p of t is just this p hat normalized to 1. Okay, so this is just exactly p hat of t divided by 1 over a plus 1 over b. 1 over tj divided by 1 over aj plus 1 over bj. Okay? So I've done nothing here, right? I've just multiplied and divided by a naught. But that sort of lets me interpret the amplitude as the expectation value of e to the minus s1 in the probability distribution given by e to the minus s naught. So this is the extremely important point. So is this clear or totally clear? Okay. Trivial point, but extremely important for how we're going to think about things. Okay. Now, this now lets us sort of think probabilistically, and that's the sort of key to making progress here. But before proceeding, I should have done this a second ago. I want to give you an example of what the answers look like, okay? Just so you have an idea of the kind of answer that we're going to get. Because it's, at least to us, it was somewhat shocking. Get this chart. So here's the claim. As you'll see, the interesting thing is that there's not one uniform formula, okay? Instead, there are different regions in kinematic space. There's different regions in this kinematic space where there's a different simple formula. Okay? But let me say what it looks like already in this limit where I've turned off the rest of the C's. I can tell you what it looks like when you turn them back on as well. But just for I mean, in fact, the formulas don't change. Largely don't change. But for instance, if all the aj, in fact, I'm going to make statements that are true even if you turn the C's back on. Okay? So you can even turn the C's back on, the internal C's back on, and the formulas that I'm writing are going to be true. You have to turn them back on, it would be order 1 over n squared. Okay? Exactly as we said, but that's all that is needed. So here are at least 2 regions in kinematic space where there's simple formulas, and then I'll tell you what the story is if we get there in general. So here are some examples of what the answer looks like. And remember, we're supposed to have the amplitude goes like e to the n something. What I'm going to do instead is write the amplitude. It's just really more convenient to write it as it's equal to a product over all j of something. Okay, which of course does this as well. I just don't want to write the log of this expression. So I'm just going to directly write the formula. Okay? Or if you like, I'm going to use a notation where A goes to B means that log A over n equals log B over n plus order 1 over n to some power. Okay, so if I say A goes to B plus order 1 over n to a power, what I mean by this notation is that log A over n is log B over n up to that accuracy. Okay. All right, so here's an example. So region 1, this is the first one that'll be most simple to talk about. Suppose all the AK are smaller than the BK for all k. Okay. Then in this limit, the amplitude goes to precisely that maximal splits formula. Plus corrections that are of order 1 over n. So that's the first surprise. Okay. One term. So you turn on the C, the polytope gets way more complicated, doesn't matter. The answer is just exactly the same thing again. Okay. A second limit. The AK are bigger than the BK for all k. And not only that, this finite quantity AK minus BK over 2C is less than 1, but increasing with k. Or non-decreasing. Okay? So I told you they're regions of kinematic space. Okay, so this should look funny. So these are why would we ever care whether AK is less than BK or these other things are true is not remotely manifest at the time we should care about these regions. And all of kinematic space is going to get carved up into regions like this. I'm just giving you 2 examples where we can write down the formulas extremely easily. In this case, the amplitude goes to the product over all j, 4 over aj plus bj. So I hope you see in a very, the sort of concrete sense in which simplicity emerges at large n. At no finite n are the amplitudes simple. You can work them out. They look like horrendously complicated expressions. You go to large n and they collapse to these one-line expressions. They're as simple as the Park-Taylor formula. Okay? But not at any finite n. They become simple at large n. Okay?
And they have this non-physical.
Yes, yeah. So can I explain something? Is that okay? There's a C here that's positive. Should we talk about that one too? So what Kelly was saying, if you look at this formula, you might naively think this formula cannot possibly be true. Because the amplitude doesn't even have poles when the a's and the b's go to 0 in general. It has poles when the x's go to 0. Well, a is an x, but b is not an x. Right? B is c minus x. Okay? So how can this formula possibly be true? It doesn't even have the right poles. Well, this formula is only valid in this region of kinematic space where a is less than b. In this region of kinematic space, you cannot reach the poles where b goes to 0, while keeping the x's positive. Okay? So, but this also shows how non-diagram-like these formulas are. They don't care about the poles. They couldn't give a crap about where the poles are. Okay? This formula is even more dramatic because none of the terms downstairs are poles. Okay? These are not poles anywhere. If you write this in terms of the underlying physical momenta, this formula is the amplitude goes to the product of 2 over pi dot pi plus 2, pj dot pj plus 2. Okay, so it looks a lot like the Park-Taylor formula, which has consecutive things downstairs, but here you precisely have the non-planar poles downstairs. Okay. Oh, and I forgot to tell you, in this case, the correction is order 1 over square root of n. Okay? Which suggests the existence of some random walk behind the picture, which is what we're going to see in a moment. Okay, so the physics at large n is associated with a picture of a random walk in Schwinger parameter space. Okay, so that's okay. Anyway, that's what the formulas look like. We are in the midst of learning how to do a systematic 1 over n expansion around these asymptotic limits. So we don't have a theory for that yet. We have sort of hints of how to do that systematic expansion. But what we do know how to do is you give me any picture of what the AK and the BKs look like, we know how to produce a formula that looks like this. And it always looks like this. It's always the product of some 1 over AJ with a shift and 1 over BJ with a shift. And we're going to explain where that now comes from. Okay? Maybe I'll make a final comment. The Catalan case is this one. Okay? We could have said it before. The Catalan case, when you set all the x's to 1, corresponds to a situation where all the c's on the boundary are 1, the corner c is 1, and all the c's in the middle are 0. Okay, so the Catalan case, where you're just counting diagrams, is this limit, is also this limit. And that ends up being, in this case, the AJ ends up being 1, the BJ ends up being 0, because it's a c minus x, and so this is the 4 to the n. Okay, so that's where the Catalan is, and this is a sort of specific deformation away from Catalan. All right. Now I think I have 10 minutes, so let me give you an idea of where these formulas come from. And so we're going to begin by looking at this picture. Okay? So to get a first intuition for what's going on, so I'm going to write A is A naught. I'll write it again in this way. Expectation value of e to the minus S1 and the probability distribution gets given by S naught. The first thing we're going to do is to try to bound this guy. Okay? This has an obvious upper bound. Right? The obvious upper bound is that S1 is positive, because it's a max of 0 and something. And the C was positive. So S1 is manifestly positive. So this is less than or equal to 1, so this is less than or equal to A naught. So we have an upper bound on the amplitude, which is that. That's already kind of cool for absolute free, right? So the amplitude is less than or equal to S naught. We also have a cheap lower bound on the amplitude. The cheap lower bound is from Jensen's inequality, right? So Jensen's inequality says that if you have a convex function f of x, it says that the average of f is bigger, the average of f of x is bigger than the f of the average of x, right? That's the Jensen inequality. You draw a convex function, and it's just sort of famous picture, right? So this is the average of f, this is f of the average. So if the function is convex, this is always true. Okay. The function e to the minus x is convex. Okay. So from here we learned that there's a lower bound. The amplitude is greater than or equal to e to the minus the expectation value of S1 and the probability distribution e to the minus S0. Okay.
Also times A0, right?
Sorry?
Times A0, right?
Sorry, times A0. Sorry about that. Exactly. Okay. All right, now let's look at that lower bound. Let's try to understand what e to the minus S1 is. Well, remember, let's write S1. Yes, there was a question? So S1 was max of 0 minus t1n minus 1 minus t1n minus 1 minus t1n minus 2 and so on. All right, and now let's think about what the probability distribution is. Remember, it has a slope that's ak for t1k and bk in this other direction. They're in general different, and I've drawn it now in the limit where ak is smaller than the bk. Okay? Just to make it clear that what does this probability distribution want to do? It wants t, t can jump forward or backwards, but it preferentially wants t to jump to positive t. Okay? So if it jumps to positive t of order 1 over a, that's not suppressed. Of course, 10 over a is exponentially suppressed. But negative t of order 1 over b is okay, of order 10 over b, anyway. So it wants to preferentially go in the positive direction. Is that clear? That's for each t individually, but what are the things that are showing up here? The things that are showing up here are precisely what you would sort of think of if I plot here tn minus 1, tn minus 1, n minus 2, and so on, tn minus 3, all the way up to t3, then, if I plot what I see here, which is, let me do it the other way. So here I'm going to plot 3, 4, 5, up to n, right? Then what I'm seeing here is here I see t, here I see t plus t, right? So it's exactly like the sums of everything before. It's like I'm doing a walk, right? A random walk from here. And what I see in every max is the sum of all the t's that came before. Okay. So if I draw this picture, it looks like, in general, I'm doing a biased random walk. Okay. If A is smaller than B, the bias is in the positive direction. I want to make the sum of these t's bigger. And it's roughly going to go linearly, right? It's roughly going to go linearly as I go up from here. Okay. If A was smaller than B for all of them, then it would go the other way. If A is equal to B, then it would sort of like randomly walk with a root n sort of fluctuation around it. Okay? But let's begin from the simplest case where AK is less than BK for all K. If I do AK less than BK for all K, then what's going on? Like this term wants to be T1 n minus 1 wants to be positive. Okay, so this wants to be negative. This wants to be more negative. So each one of these things wants to be more and more negative. And so the max is dominated by 0. Okay. So this is why it matters whether AK is bigger than BK or less than BK or so on, because the sign of the drift of this random walk is going to matter. Okay? But when the AK is smaller than all the BK, the max is dominated by 0. That means that we're talking about at order n, the max is going to be order 0. It can't be order n. The max will be order 0. Okay. And therefore, this lower bound this thing is e to the minus order 0. Doesn't have any n's in it. E to the minus order n to the 0. Okay? Well, that's fantastic. We have the amplitude then at leading order at large n. We've bounded it between two numbers, a naught and a half a naught. You know, some number of order 1 times a naught. So that tells us that that log of an over n approaches log of a naught over n plus corrections that look like 1 over n. Right, so that's our first super cheap prediction. Okay? It's already very non-trivial from the perspective of any other normal perspective of the boundary diagrams. I should say that these predictions have been checked. How do we check these predictions? This theory is simple enough that we can use normal recursion relations to compute the tree amplitudes. Okay? You can do it if you're not good at computers on Mathematica up to n of like 200. If you're good at computers, you can do it up to n of 5,000. Okay? And we've gone up to n of around 5,000 because we need to. These 1 over root n's are errors that we should expect. And 1 over root 100, if the coefficient happens to be 3, is not necessarily a small number. Okay, you can get confused. So we really needed to go to n of a few thousand. Okay, so every formula that I'm telling you has been checked up to n of a few thousand. Okay, and they're correct, and the errors are correct. Okay, as sort of we would predict from this picture. But anyway. So that's the most trivial. That's the most trivial example. Maybe just in 5 minutes, let me give you an idea of how we do things in general. Okay, so for example, let's say AK is bigger than BK. Let's say AK is bigger than BK for all K. Then I just erase it, but the drift is going in the opposite direction, right? That means that the expectation value of S1 is of order n, right? That means that this bound is absolutely lousy. Right? These bounds are totally useless. The amplitude is less than 1, is bigger than e to the minus n, so it's utterly useless. It just tells us between 0 and 1 in these units. So that doesn't tell us anything apart from the upper bound. But our reaction to this is that, in fact, what's wrong with this is that the upper bound was too stupid. Okay? We did too lazy a job with the upper bound. We're going to find a much better upper bound. Okay? So I'm now going to tell you how to find a much better upper bound. And it's a little bit of magic that this optimal upper bound happens to be saturated at large n. Okay, so that's some separate arguments, but I'm now going to just give you a new way of getting an upper bound. And the remarkable, at any n, but the remarkable thing is that this formula for the upper bound at any n turns out to be the exact amplitude, the leading amplitude at large n. Okay? A conceptual reason why this happens, we still don't know. It feels like some ergodic explanation should be available, right? Somehow the amplitude is filling up some phase space, maximizing some phase space, some words like that. We don't have one-line conceptual explanations like that. We do have relatively simple proofs that have very much this character of looking at these random walks and thinking about what happens with these random walks. Okay, but anyway, let me tell you what the argument is. It's extremely simple, and this is something I would be astonished if it has not come up in many other places in mathematics. I'm sure it has, and it would be interesting to compare to the setting that we're seeing here. Okay? So I want to come up with a better upper bound. And so you see, my formula was S1 was the max of a bunch of things. You know, C times the max of, and let me just call them some cap A1, A2, A3, etc. Right? One of these happened to be 0 for us. And so we said this is like saying max of A1, A2, and A3 is greater than or equal to A1. Why do we choose this one? There's no reason to choose that one. Okay? I could put here A2 or A3 or anyone else. For that matter, I could put any weighted average of them. Okay? And the max is bigger than any weighted average of them. Okay? So that's what we're going to do. We're going to say that S1 is greater than or equal to W1A1 plus W2A2 plus W1AN, where these are positive weights that add up to 1. Okay? And so that means that the amplitude is for any choice of weights is still upper bounded by what I get if I did that. Okay? But you see, the nice thing that happens the moment you replace S1 with this weighted average, the maxes are gone, and all the variables are decoupled again. Okay? So I can do the integral. So all the variables are decoupled. Okay, so what do I get? Well, it has its extremely simple interpretation. Let's just see what it is here. Where did my pen go? Oh, I left it in here. That's great. Sorry. That's really yellow in there now. That's great. So let me erase this. So leave that to dry. Right down here. Okay, so the amplitude is going to be less than or equal to, again, this integral of the dt's, e to the minus s naught, but then I'm going to have e to the minus c times wn minus 1 t1 wn minus 1. I'm going to call the weights for the terms labeled by the smallest t that occur. So plus wn minus 2 times t1 n minus 1 plus t1 n minus 2 plus, and so on. So plus finally a w3 times t1 n minus 1 plus t1 2. Okay? And there are minus signs in front of all these guys. So the maximums have the negatives in them. Okay, so there's a negative t1 n minus 1, negative all of these guys, plus w3, negative all of these guys. Okay? And so here I just replace S1 by this weighted average. But now you see very nicely, again, all the t's are decoupled again. So every t integral has some effective new aj and bj. There's an effective new aj and bj. So this is equal to integral dt1j, the product of all j, of some p of some a hat j and b hat j, where what are these a hat j's and b hat j's? For example, t13, the only place anything involves t13 is this weight w3. Okay, so we have that a3 hat is a3 minus w3 times c. Okay? This is there's a minus sign, so there's an e to the c t13, but there's an e to the minus a t13, so a hat 13 is a13 minus w3c, b hat 3 is b3 plus w3c, but then a hat 4 is a4 minus, and there's two w's, there's w3 plus w4. That touches 4, b hat 4 is b4 plus w3 plus w4. And in general, we can say that a k hat is a k minus c. We can call it sigma k, where sigma k is w3 plus w4 plus all the way up to plus wk. Okay, and b hat k is bk plus c sigma k. Okay, and therefore, what we're left with is that this mu upper bound on the amplitude that depends on these weights is that the amplitude is less than or equal to, since they're all decoupled again, it's just the product over all the k's of 1 over a hat plus 1 over b hat. So I'll write it in terms of 1 over ak minus c sigma k plus 1 over bk plus c sigma k. Okay. So for any choice of weights, so for any choice of w's, any choice of weights, this is a true statement. Okay. Now we can, instead of working with the weights, we can sort of nicely directly work with the sigmas. The weights being positive means that the sigmas are positive and increasing, right? Because the sigma k are sums of consecutive sigmas. So I can not talk about the w's, I can just directly talk about the sigmas, but say that I have 0 bigger than sigma 3, sigma 4, less than sigma n minus 1, less than 1. Okay? So I can give sigmas, or I can give weights, or I can give any choice of sigmas in this range. Okay? And so now comes the point. There's a best possible upper bound that I can find. Right? The best possible upper bound is to just minimize this function over the space of all sigmas that satisfy this property. Okay? Okay. So let's see what that means. If I just take this, note that the AK hat plus BK hat does not depend on the sigmas, right? The sigmas cancel between these things. So if I just looked at this and said, where is the global minimum of this function? Where's the global minimum of this function? The global minimum occurs at some value, let's call it sigma k star, which is equal to AK minus BK over 2C. That's where the global minimum occurs. Okay? So if you can attain that global minimum, that's the best upper bound you can find. Okay? But you have to, but the minimum, so either you obtain the global minimum, or if you can't, you have to find the minimum somewhere on the boundary of this space. Okay? So let's say we go back to our previous problem. When the AK, what is this doing? This is just the sort of, famous fact. You have a 1 over A plus 1 over B. Right? The sum is constant, so they just you want to tune sigma to make them equal if you can. Okay? So, but let's say we go back to our previous example. If AK is less than BK, then, well, this sigma would want to be negative, which we're definitely not allowed to do. Okay? So in the case where AK is less than BK, the best you can do is to do nothing. Okay? Because anything you can do with these sigmas will hurt. So the optimal upper bound is to put all the sigmas equal to 0. Okay? That's our previous formula. But you can ask, can we sometimes get the optimal, just the dead optimal case? Yes, you can. If this is realized, by the way, if this is realized, the sort of A star absolute optimal would equal the product over all k. If you shove this in, you get precisely the formula that I had before. 4 over AK plus BK. Okay? But when can that be realized? When these sigma stars live in this space. So that's what I told you before, right? It's when AK minus BK over 2C is bigger than 0 and increasing, right? Which exactly means that it lives in this space. Okay? So these are sort of two extremes where this upper bound, where you can easily figure out what the best upper bound is. And so we get this best upper bound, and the claim is that the amplitude is saturated by that best upper bound. In fact, the way to prove it is to really return to this picture. And instead of saying that I'm giving an upper bound, just say that I have the action as S0 plus S1, but I'm going to rewrite S1 as S1 minus this sort of approximation to it, the sum of the weights, max of the, the max of the corresponding sums of negative t's, plus the same. I'm going to call this whole thing S1 hat, and I'm going to group this. I mean, this is the piece where everyone is decoupled. This and S0, I'm going to call S0 hat. These will depend on the weights. This will depend on the choice of weights. And now I have a new interpretation where the amplitude is equal to A0 hat multiplied by the expectation value of e to the minus S1 hat in the probability distribution e to the minus S0 hat. Okay? So for any choice of weights, we can have this probabilistic interpretation. And what you can then show is that when you choose the optimal choice of weights, then this e to the minus S1 hat is always of order 1. Okay? So, and that needs some more argument to sort of thinking about drifts and random walks. But you can see why there's a correlation between optimizing this upper bound and getting this to be order 1. So it's not an accident that the two things happen at the same time. Okay? Okay, so that's, I think, all I will say about this. I've gone over time. But there's, just to say something quickly, this problem of optimizing this product in this little region is a very, very pretty little high school problem. Okay, so if you have just to give you an example, let's just plot I'm going to plot what is AK minus BK over 2C. This is this sigma star. This is an important quantity. I'm going to plot it as a function of k. So here would be k of 3, but I'm going to go 0 to n. Okay, I'm going to draw it in a continuum. So 0 is clearly special. 1 is clearly special here. Okay. So if the AKs were less than the BKs, you're down here somewhere. And the optimal is sigma equals 0, right? That's what we said. If AK minus BK is positive, but C is still so small that this quantity is up here somewhere, then you're in the opposite limit. I mean, you want to make the A and B equal, but it's so far to get there that, you just take a little step in that direction and sigma's already maxed out at 1. Okay? So what you can do is just keep sigma at 1. Okay? But if, on the other hand, the AK minus BK over 2C, if the kinematics looks something like this, it's increasing in some way, then that's what you can call this tracking solution. Then the optimal, the pink curves are here what sigma looks like. The sort of optimal, the sigma k's that optimize the bounds will sort of just track it. Okay? But in general, whatever the picture for the sigmas are, has to be some increasing picture here that's bounded between 0 and 1. And as we learned in Europe in junior high school probably, in the US in college, when you're minimizing a function on some compact region, again, either the minimum is in the interior or it's on the boundaries somewhere. Okay? And what does it mean to be on the boundaries here? On the boundaries here, if you're drawing a picture of the sigmas, means the sigmas are just going to be constant for a while. Okay? So the bunch of sigmas can be equal. So they can be constant or they can be increasing, but they can only be increasing if this curve of AK minus BK over 2C is increasing. So, for instance, if your picture of AK minus BK over 2C looks like this, let's say it's decreasing, then the best you can do is just keep sigma at a constant somewhere. Okay? So that's what the boundary looks like. Sigma can't go up anywhere because that would correspond to it being in the interior, right? But it's not. It can't be. If it's going to be on the boundaries, it's got to stay constant. So the best you can do is just choose some sigma star and then just plot that quantity as a function of sigma star until you find the optimum. And that gives you the formula for the amplitude. So it's not like there's an analytic formula you can write down ahead of time. You have to solve this little optimization problem. But this optimization problem has nothing to do with n. You just draw me the smooth curve, and I just take this product and I minimize it. Okay? So, and so if you have a more interesting situation, let's say you have a curve that looks like, it looks like this. That's what AK minus BK looks like. Well, down here, the best you can do, as we saw before, is to keep the sigma 0. Now the AK minus BK is increasing between 0 and 1, so you can track for a while. But you can't track forever. So at some point, you've got to stop. At some sigma star, you've got to stop and say, no, now I'm going to go flat. I can go flat until the next time the thing is increasing, and then I can try to increase again. And then here it's going to flatten out again. Okay? So this is what your ansatz for the sigmas has to look like. And then you optimize again. So again, there's not an analytic formula, but the cool thing is that it has nothing to do with n. The limit has to do with the number of humps in the picture for AK minus BK. Okay, the more and more humps there are in the picture, the more and more parameters there are in your optimization problem. But for example, in this case, there's one parameter. So you put it on the computer, you plot it, you find sigma star, you shove it back into the formula, and that's the amplitude at large n. If it looks like this, there's this point. Well, okay, there's really still only one sigma star here. So you just you vary the sort of point in which this escape could happen, and you optimize, you minimize this product. So that's the sense in which there isn't an analytic formula at large n, but kinematic space is broken up into regions that correspond to sort of qualitatively different ways that this optimization problem can be solved.
Is it possible to make a last question?
Yes. Yeah, that's all I want to say is this. Yes, but what is your question?
Okay,
Yes.
so how universal are the grid-like structures? How universal are those grid-like structures? How universal are these formalism string theory derived grid-like structures? In other words, how does all of this translate to a more complicated combinatorial object derived from physics? I mean,
well, I think the answer is going to be a little similar to answers I gave to earlier questions.
Yeah,
the whole model to begin with, is a toy model. Naively, it's surprising that the toy model ends up being connected to very physical models in a non-trivial, in a very simple but not non-trivial way. One thing I will say is that there is something very universal about what we're talking about. All of these x's are singularities. All these x's are poles of amplitudes, and those poles are there in every theory of colored particles. So that part, the sort of singular part, is totally universal. Is there for any theory that has a color. So gluons, pions, all kinds of theories that have a color will have those poles. That was a big motivation for studying these things a long time ago. They were super duper simple, but they had some universality in their pole structure. That thought would make you think that to get to realistic theories, you have to do a lot of work to get the intricate structure of the interactions that show up in the numerators. And the big surprise is that all of that intricate structure of the numerators turns into exactly the same formula, just shifting the variables in some ways. Okay?
yes.
So just to make this a point, I didn't say what the specific shift was to get to pions from this scalar theory, but there was a simple shift to get pions, and it gives rise to formulas that are virtually identical to these formulas for pion amplitudes. Okay, so that was.
Can I say just one thing?
Yes.
Because I have to leave, because if I get too late, I'm going to get expelled from this class.
That sounds very dangerous. Yes.
Yeah.
Right.
I have I sneak a lot into places, and sometimes I sneak into this IAS website at 3 a.m. just to have fun little and see what people are doing. So like 7 months ago or 8 months ago, there was this colloquium about a colloquium about combinatorial objects. I don't recall the exact title of it. It was very recent, and I remember that I was just messing around on Quora or Reddit, and they had.
Can we answer this question later? Because I'm sorry, because I had a few points, and we're over time already for my talk.
Yeah.
But there was one more physics point I wanted to make, and I want to give people an opportunity to ask questions about the physics. You're not asking questions about the physics that I'm talking about. We can talk about it later, but you're not talking about the physics. So let's. Can we just put this aside for a moment, please, and just talk about it later? Thank you. Yes, go ahead.
Yeah, just a quick physics question.
Yeah.
So, do you see any relation of this kind of to people in cosmology have studied kind of these tails of a PDF, especially also for kind of primordial black hole formation?
Yes.
Anything rings a bell there? Like what?
I don't know enough technically about what they're doing to know if it rings a bell to you. Let's talk about it. Yeah. I'll just say just very very quickly that adding the C's back in this picture is I hope it's kind of clear. For example, if we did the AK less than the BK problem, it's clear all the other C's still involve maxes of 0, negative t, so they're all going to be near 0, right? They're all irrelevant. So it doesn't matter if you add them back in or not, okay? So long as they're order 1 over n squared, so 1 over n squared of them doesn't give you something of order n, it gives you something of order 1. So it does matter if the C's are of order 1 over n squared. If they're of order 1 over n, it wouldn't work, okay? But if the C's are of order 1 over n squared, it does work. And since Bern asked, the version of this idea that you use for scattering equations for string amplitudes is the non-tropical version of the formula that the max of A1, A2, A3 is bigger than the weighted average of the max is the arithmetic geometric mean inequality. Okay? So we take all of these formulas, and so now we have polynomials, A1 plus A2 plus A3 to some power. Okay, and this is what makes it complicated, but we use the fact that A1 plus A2 plus A3 is greater than or equal to A1 over W1 to the W1, A2 over W2 to the W2, and so on, right? A3 over W3. So this is the pre-tropical version of the statement. And once again, this decouples all the variables. And you can do all the integrals, and it gives you something new to optimize over the weights. What's fascinating is that the new thing that you optimize over the weights, the optimization formula is like another set of critical point formulae, but they're not the same as the scattering equations. However, they have exactly the same solution and exactly the same value of the action at the critical point. Okay, so that seems very interesting. And this new form makes it much easier to analyze the large n limit. That's the point. So the scattering equations themselves look very complicated, but these are much simpler, and the large n limit lets you isolate the solution, which is relevant. And that seems like something worth thinking about. All right, thank you very much. I'll stop.